So we start our next topic, which is called kinematics. And here what we'll be doing is we will establish the foundation of describing the motions of material, let's call it material points. We'll talk about it just very soon. So, and what we're going to define here is still rather generic. So we're not going to say, okay, so metals deform in this way, rubber materials deform in that way, biological tissues, soft tissues deform in this way. So what we are going to define here is still will be a general description of, let's say, any continuum. And then only later on we are going to specify the particular material behaviors, how they come into play. So this is in general kinematics of continuum. Once again, this is not material specific and still rather generic. That can be used in different frames of describing different material. Now let's start. And so, right, one of the important concepts that we need to introduce here, so we have a good understanding between us what we're actually dealing with, is the concept of so-called material points, right? So or material particle, if you like, which in probably material point is a better term than material particle, because then that particle you can somehow relate to what we don't want it to be related. So I don't want you to think about atoms or anything that the material is made of, molecules or what's not. So we are basically thinking about the material as having so we're not looking into the very small length scales of how the material is structured from atoms or molecules. We are treating the material in terms of some sort of effective properties that stem, of course, from the, say, molecular or atomic or crystal structure, but we're not looking into these details. So for us, the properties are important, but where they come from, we're not that concerned with that. And we introduce that concept of the material point when that material point probably, if you think about it in a more philosophical sense, includes quite a lot of elementary particles in there, right? Say atoms, but this region, that piece of material that we start calling material point, is still small enough for us, so that we can call it, mathematically speaking, a point. So basically, that kind of naturally comes to us to say that there are different length scales. So there is a length scale of when the material start to be kind of discrete, right? So there is probably space between atoms, let's say, in a crystal lattice, if you like. So we don't want to be there. So we want to be able to treat our material as a continuum. So there is not space in between. So this is a continuum material. It's a continuous material. And that's we define this. So we adopt that, and then we follow all this concept of material point once again. It just we need to understand that there is a limitation between length scale, so we cannot apply this continuum hypothesis to small length scale where that definitely will not apply, right? And so again, so a good example would be you can come up with many examples, right? So with different length scales. So if you, for example, we talk about a piece of rubber, right? That's just simple rubber eraser. And that you can bend that, and then from simple consideration of bending of that rubber eraser, you can understand that the deformation that happens, distribution of stresses, basically deformation, varies with the radius, and basically the length scale of what happening there is length scale of let's say, millimeters. But of course, we know that rubber is made of, so there are lots of long molecular chains, so networks of these, so they interact at the at these length scales. It's a and that but that length scale will be really very small, right? I know, somewhat of several nanometers. And for us, this is irrelevant. We're not going into the considering such small pieces of material. So we are considering a larger material. And so and so it's important to that we understand this difference, and we don't go there, but we also don't really draw a very sharp line separating this length scale. So this is a number that is too small, this number is too big. It also depends on, for example, on the size of the body that you consider with as a boundary condition. So what would be the reasonable sizes to consider or not. Again, so this is just an introduction to that. It's more like a building intuition, but I need to say these few words. And here is a few examples of, like, okay, so for different systems there are very different different numbers of particles, elementary particles, that will be included in the same volume of, for example, a centimeter cube. Right, so for iron is by far more dense packaging of atoms, 7 orders of magnitude as compared to the air, very high high point from the Earth. So, okay, so we're taking extreme examples, right? So in space, the number of particles. So that is where you definitely lose any ability to apply it as a continuum hypothesis, right? So, but taking that to a very extreme thing. Bottom line, let's say so basically what we do, we assume that there is a separation on length scales. So yes, we do know that there are atoms, there are molecules, or chains of polymers there, and they basically define the properties of the material. But we are now not concerned with chemical composition of that, etc. We just we treat this at a little bit somewhat larger length scale. So we zoom, so you kind of didn't zoom enough if you had that microscope to actually start seeing these polymer chains and everything. So you still see some continuum, you just see the material. That's probably one of the ways to look into that. All right, so with this in mind, so then we will be operating with the idea of that, so that we can come to any point and still follow this continuous material, and what happens to that. So we have this material point. All right, now here it comes that the schematics that almost any course in continuum mechanics come to a certain point, as this typically drawn much better. So we will have these two potatoes. Right, so that's of course here that they don't look like potatoes, but well, so this potato number 1 or number 0, and potato number 2, or the potato that the initial potato will be deformed into, and therefore, so we call this initial state, or we call it a reference configuration or undeformed configuration. So that's where we start from. And then so after we did something to the body, we applied loading maybe, or some forces or gravity worked on that, and that was too soft, and the material deformed, and so that occupies a new configuration. And so that old configuration, that initial or reference configuration or undeformed, we call omega 0, and the current configuration, that will be that omega without 0, right, to differentiate between them. And of course there can be different notations for that. So some would use, for example, in the literature, some fancy B0 and B that without 0. Now all that happened in some coordinate system, and for the simplicity, and well, we already considered that we can have anything else, but well, let's talk that this is happening in the Cartesian coordinate system. But there is we don't lose any generality by introducing that in Cartesian coordinate system. So with that, we can identify each point here in the undeformed configuration with its position vector x, and let's call it x for that, right? And now then we can track each point and see where it goes to. So that point, for example, goes to the new position, to deformation. That position will be identified by the position vector y, right? And so this is important. So now we need to find a way to connect each point in this undeformed or reference or current or initial configuration, and we need to find a way to find this mapping between what was in the undeformed configuration and where this point and any other point goes into this deformed configuration. All right, so let's give it these names. Again, x will be referential position of material point, and y is the current position of that material point. And again, there can be different names. I will mention that again later on the next slide. So it can be called, reference can be undeformed configuration, and y can refer to the deformed configuration. Typically two names that I used. And also the Lagrangian and Eulerian description that, again, we'll mention it right next. And now you can think, this was again just for us for looking for one particular point, right? But this position point, right? So x basically can be related to any point here. So right, any point here is characterized by its own position point x, right? And therefore the mapping is defined in a very simple way, right? So that is at any given time t in the deformed configuration, so the new position of that point can be somehow related to this position vector x, right, in the initial configuration, right? So each point, right? So that's why it's point. This is the function of x. So for each point x here, there will be some new coordinate in the deformed configuration, right? So we'll use that. And one note that I would like to also make here. So sometimes in the literature, again, so that because the notation is not really, it's not a law, right? So it's again our agreement of how we use the notation. Sometimes in literature, and actually quite popular, I would not say which is really more popular. The people use the following agreement. So sometimes they use whatever is in this configuration, in the undeformed or the referential configuration, they put 0, they add that 0 sign here, or subscript or superscript sometimes, so again depends on the preference, and then they use exactly the same letter for the same quantity in the deformed configuration but without 0. So for this case, for example, they would put x 0 they put 0 here, and instead of y they would just write x. Another notation that is possible is to use, for example, large letters for anything, for things that are related to the undeformed configuration. So that would be capital X if we would follow that notation. And then for this configuration, instead of y, they would use small x, so kind of distinguishing between these two configurations. So this again just for you to know. So when you go to the literature and read something about that, so you will know. We will need to figure out from the beginning. Typically, the authors do say what notations they use. So this is not a universal notation, and this is of course not a law described by nature that we need to follow. This is just our agreement. All right. So again, reference and count configuration. So different additional names for that are, referential or material description, right? Or that what, and also in sometimes in the literature, not on, quite popular, would be mentioned as Lagrangian description of motion, right? So what happens is that we do hold x as independent variable, our initial point, right? So this is our independent variable. However, the equally applicable and absolutely valid approach is to consider y as an independent variable, like right in the undeformed configuration, in the deformed configuration, and that approach is known again. So that could be description, Eulerian description of motion, or spatial, right? So or current. So and so okay. So the names are, that's why we have these faces here of Lagrange and Euler. So basically, you will find that using the initial or referential description or material description is makes more sense in the cases when we work in solid mechanics, where in a way what happens is that, again, thinking about the materials, that you know where you start from, you have your body, and so initial boundary can be described, you know how it looks like, and then you apply some loading, some forces on the boundary maybe, and or that can be again body forces, gravity working on that, and then that body will deform into something that you don't know. And if you don't know that, so it's harder for you to describe where and what you applied in the deformed state, because you don't know how that would look like, right? So that's and hence, so that's a motivation to go with the Lagrangian description. And so for the Eulerian description is probably would be more popular in when you would describe the motions of a fluid, right? So because they have a different that area would have a different concept of defining the boundary condition. So you know the way it would be, for example, if you talk about the pipe, and so then you would follow. So then you can, again, you can follow and measure everything at a point, or you can follow the material point and measure everything in as the point moves. For example, you can measure a change in the density, or you can measure different changes at that point, right? So you can follow that, you can track and go with the point, and as if you're sitting on that point, and that you will be measuring, right? So that would be another approach, right? Or you can just say, I will measure how things change, not at the material point that moves, but just at some point that doesn't, right? So that fixed in, for example, some location of the cross section on the tube and through which the flow flows. Anyway, so this is just to mention that. So there is difference again. So if you encounter something in the literature, so there is this is difference, and these approaches can be used in both in both fields. Okay, so yeah, so there are quite different pictures of Leonard Euler. So I will not talk about much about this. So this already from a more for a later stage when he would partially lost his vision, so that's why he looked a little bit funny here. Okay, now let's talk a little bit more about back about the kinematics and the problem in particular of how we are going to measure the measure the movement of these points, and at the end, of course, we want to describe what is going on in each point. What basically we are going after measuring the deformation at a point, but then the question is what is the deformation at the point, and so therefore we need to define some element that we will measure what's going on with that, so the deformation of those elements. So point is not a good thing to have to measure deformation, right? So how a point would deform, that's not an easy question to answer. So, but we can define some elements at a point, right? So, and then follow that the deformation or what's going on, what happens to those elements. In more, in particular, let's us define these elements is these tiny arrows here. Let's call dx, and this is how it transforms into dy. And before going further, let's just say what this it is. So let's say we have some small, we can call it line element, but kind of to connect it to some physical meaning. Let's say this is a small tiny fiber at that point, right? So at that particular point we identified some line element or some small fiber, and it's really very small, infinitesimally small. It's not a point, it's a fiber, it's a line element, so it has a length, and that's important for us because we actually are going to measure the change in that length, and we're going to associate this with the deformation, the change in the length of that line element at the point. Now this is of course a vector, right? So we the line element is associated with a vector, right? So it's not a point, it's not a scalar. And now we can then define what is called the deformation gradient that will relate these two vectors of the initial line element or initial very small infinitesimal fiber into its vector in the deformed configuration. So that's where we started. Then we applied something on the boundary. The whole potato deformed into new configuration, and so now we are following that point, and we're following that small fiber, and we see that something changed. So then changed the orientation and may change also the length. And so to map that, we have that connection F. So basically what we did, again, this F is a second order tensor, so we have a second order tensor F that acts on that dx vector and maps it into new vector dy. Right? So again, connecting us to the concept of tensors, that what they do as an action, that they map one vector into another. And now so the F is not a randomly defined, it's not something that we can define freely. F has an interesting and important structure and definition. So again, it's also called deformation gradient, once again. And that is defined as a gradient of that mapping y, right, of the new position as a function of x. And well, as we already mentioned, so each y is a function of x, so right, so the position in the current configuration is dependent on the on each point is related to x, so that is a function, so therefore we can take the derivative. And again, so now we're already using the structure that we know how we define the second order tensor, right? So here is the dyadic product, this of our basis vector, so this second order tensor. And so in the components just take the derivative of the position vector in the current configuration with respect to the position vector in the undeformed configuration or reference configuration here. Now, I will mention that here that uh, sometimes this deformation gradient, again second order tensor, is called what is called the two-point tensor, and in a way it can be seen from here because it's a tensor that you can imagine that has one leg that sits in the current configuration and the other leg that sits in the undeformed configuration. And so that also can be seen if we, for example, if we had the all right, going back here to this description of the potato, so we could say we have vector x here, right? This is for undeformed configuration. Let's call it e1 and 2 and 3, so that's the coordinate system. But we also could define our new vector y through its own coordinate system, and that we could use, for example, capital letters for e1 and 2 and 3, and then we would have small and capital here. But because they're basically the same, the coordinates are coinciding, and these are basic unit vectors. So and so we don't see this explicitly, but in a way, so deformation gradient is not defined only in one configuration. It has that's why it's called a two-point vector, two-point tensor, right? So because it relates two different configurations, the reference and current configurations. Now we can look into what actually deformation gradient is composed of, and what we can notice is that actually there is one more vector here that we didn't introduce just yet, right? But that vector connects these two vectors x and y, so the original position and the position in the current configuration or in the deformed configuration. Now this is in general something that you're very familiar with, is a displacement, right? So that's how you displace your your vector here, this point x into y. And basically you can see that y, the new position vector, is just takes the position vector, initial position vector x, plus the displacement vector, and then you will obtain your the current position vector y. So therefore we can go back to this definition 2, and instead of y we can just write that y is nothing but x plus u, right? And so then now looking into this, what we have here, so we take the gradient and of x, right, again with respect to x. So the result will be the identity tensor here. So this first will produce the identity tensor here, and the second one will be the gradient of u. And this we denote it with h. Again, so that can be different, but some literature does follow that, and we call it displacement gradient, right? So this basically grad u, and the structure is again the same. One more note here, which is important, is that as you might notice by now, that for this differential operator gradient, we suddenly started writing it from the capital G. And the intention is such that, because already so we already noticed that there are two configurations, so there are two coordinate systems, right? So that can be, right? So it can be, there are two coordinates x and y, so we can choose whether we want to take the derivative and calculate the gradient with respect to y, for example in this configuration. If we want to see, we can calculate gradient here, or we can do this with respect to x in this configuration. And to make it, to distinguish that, so we use a capital whenever we want to do a differential operator in the undeformed, in the reference configuration, meaning with respect to x. If we will want to do that with respect to y, so then we will use a small g here for gradient, or small letter, if that will be, also it can be divergence or rotor. So this is again an agreement and the notation that we follow. Right, and then again looking into the structure of displacement gradient, so this is again the second order tensor. The components here are given like this, and so we're already very familiar with how we write second order tensor in terms of the tensor product, the dyadic product of the basis vectors and the components here. Now, so with that we can proceed to actually describing the deformation, right? So that's what we wanted to do. In each point we wanted to say what changes, how the things change. And so we can, in fact, we can identify three useful parameters for us to change at this point, just kind of an example if you like. So we can look into the three-dimensional case and change the and look into change of the volume, right? So that will be, so we can monitor that around of the volume, of the very small volume around that point. So a change of the volume at the point. We can look into also into the change of the area, that kind of go into 2D, and then we can also monitor the change of the length of that fiber, of that element, and so that will be the line element, and that we can look at. But let's start from the volume. So that is a very natural example for us. Okay, so a volume can be built. So we can build a volume based on just on a bunch of vectors, right? So that's there's our three vectors that allows it to build some volume. And again, we kind of here zooming in. So there is a point here, and at that point we identify the initial volume, right? Which is based on these three vectors, dx1, dx2, and dx3. And here, although that may be confusing, but I want to emphasize that x is bold, so meaning that this is an independent sum vector, x1, x2, and x3. So 1, 2, and 3 are not really components of that, also may look a little bit like that, but they're independent vectors, and this 1, 2, 3, they're more of an indication of a name, right? So that's we could actually give different names for that, but we still want to keep x. Why? Because I want to associate that with the undeformed, with the reference state. And so there is an initial volume dv0. Okay, let's put 0 this for referential measures. So, and we can calculate it based on knowledge of what dx1, dx2, and dx3. But there's some just arbitrarily chosen vectors for us. Now, after deformation occurs, and deformation gradient also can change from point to point, but at this point, let's say that is f, right? At that point that we're measuring the change of the volume. And so that means that we can apply that f to see how this volume transforms through following the deformation of these vectors. So dx1 is, for example, transformed in dy1. Again, how we sketch it here, this is an arbitrary deformation, right? So we don't really specify that. So it just is schematics for this. So it can be anything, right? So dy1, so dx1 transformed into dy1, dx2 into dy2, dx3 into dy3, and how they are transformed into new vectors depends on what is deformation that is happening or occurring in this point, right? So deformation gradient. But the relationship between x and dx and dy vectors can be given through the deformation gradient like this. And again, so this m here and m here represent 1, 2, 3 is just basically indicating the kind of names or labels of each of these vectors. So these are not components; these are independent vectors, right? And so now, so what we're going to do is just we're going to calculate the volume, which we can do based on the all the vectors, calculating certain determinant of these vectors, of the matrix that can be built on these matrices, on these vectors. And so let's calculate that determinant and calculate the volume. We're going to look into dV, so just for our derivation purposes, we could look into dV0, of course, separately, but let's start from dV. And so to calculate the volume dV, we basically need so one of the ways is just to write a certain matrix and calculate the determinant of that, right? So that is based on these vectors dy, d2, and d3, right? So and this is the determinant of that components of the matrix, right? So what do we have here? So the first row here, the first line here is the components of our vector dy1, so the dy1, 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 and this is component 1 of that vector, component 2, and component 3. So this is the second row is the components of the vector dy2, okay, dy2, dy2, and dy2. Again, this 2 is just a label, just the name of that vector, and this 1, 2, 3 are actual components of that 1, 2, and 3 here, right? But here inside this 2 is a label, is a name of that vector that helps us, one of them that helps us to build that volume, right? And again, it's y, so y meaning that we are measuring the volume in the deformed state, so dv without 0. And here again, dy3, 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 so that this third vector and the components of that third vector, first component, second, and the third component. Now, all right. So this is very good. So we so somehow, if we know them, we can calculate. Now, the volume, in the deformed configuration. And again, we're not particularly interested in the value itself, but rather the change, the difference with how much it changed from the undeformed to deformed configuration, right? So we're not. It's kind of pointless for us to ask what is the volume at that point. So it depends on, okay, it's a small volume around that point. Doesn't matter what it is. What is important is how much it changed as the material undergo deformation, goes from the undeformed to deformed configuration. All right, so we are after after the change first, right? And so now, again, going back, this dy, we can express all these vectors in terms of their old counterparts, right? So in terms of this vector dx1, dx2, and dx3. And how we do that? With the help of the deformation gradient f, right? So, so this is the relation that we already established between them. And so now we can go into this matrix to calculate that volume, and actually substitute each of these in terms of the this multiplication of a deformation gradient with the old one. Okay, so so this is 1. So this is 1, for example, for this line. So for this part, and now then what we will have here is that for the component 1, there will be as we multiply it f, right, again with that dx the components, so we'll have, for example, 1 here. Okay, let's just give it look into how it looked like. So let's look into that one component. So this is again the name, so that's why we keep parentheses here. So this one is not an index, but component 1 here of that new vector dy1, it will be f1 j. So we need to do a summation here, but this is again our usual thing that we do, right? So we could write the new vector dy1, right, as a multiplication of f and dx1, and then the first component of that will be such that we'll put here an index I equal to 1, right? So that is exactly here, that I equal to 1, and j and j, here is where we have a summation. So if we write this term explicitly, we'll have f11 multiplied by dx1 1 plus f12 multiplied by dx1 2 plus f1 3 multiplied by dx1 3, right? So this is again just the exercise that you go over and over again as you do that, right? And so as we did it in tensors, right? And so you can write in a very similar manner the second component. Again, the only thing that will change 2, and you have the same summation jj, and of course we're talking about dy1, so of course the related index, the related vector in the undefined configuration x1, that's why you have x1 here all the time. Okay, so then this corresponds to dy2, so then that's why you have dx2 here, dx2 here, dx2 here. That's the mapping of the dx2. And the same with the third line, so this is dy3, the vector, right? So with the name dy3 in the deformed configuration, in the undeformed configuration it wants dx3. And so here's are just components: is component 1, component 2, and component 3 of that new vector. All right, and then now by looking into that, so we can actually conclude that we can rewrite this bigger determinant, right, as a multiplication of two determinants of two matrices. So just by using the definition of the properties of determinant, and the structure that we have here is that, okay, so we can write it in this way. So the one that will be composed of the components of each of these vectors. So these are components of dx1, right? dx1, dx1, and dx1. So it's first component, second, and third. And so this for dx2, first, second, and third. And these are components of dx3, 1, 2, and 3, right? So this is and now if we multiply this guy dx1 1, the first component of vector dx1, with the with the column here f11, 12, and 13, right? So we exactly obtain the summation that we wrote in here, right? So if we, again, what we obtain here, f11 dx1 1, f12 dx1 2, f13 dx1 3, it's exactly as the result of this multiplication with this column, right? So and a similar, you can check since the structures obviously follow it for other entries in this resulting term. So what does it give us? So it gives us an interesting notion that then what we have here is actually nothing but the calculation of the determinant of the same structures we had before for y1, y2, and y3. So it's the structure that exactly give us the the deformation, the volume, that small volume element in the undeformed configuration. So that volume that was built on this set of vectors x1 and x2 and x3 in the undeformed configuration. So the dv0. So that is dv0, and this is and this is nothing but the components of the deformation gradient f. So this is if we calculate so this is the determinant still, and so that's nothing but determinant f. So what we can write initially, so we start from dv. So dv in the deformed configuration is equal to dv0 multiplied by determinant f, and and this is a very important result for us. So because and here we introduce a new name for the determinant f called j, right? So let's give it a name. So the determinant of deformation gradient f, we will call it j, and it appears that j, determinant of deformation gradient, relates the volume in the deformed and undeformed configuration, right? So this is the volumetric ratio, change ratio, right? J represents how much the volume has changed, right? So we can just divide dv by dv0, and that will give us exactly j. So it's an interesting property of deformation gradient that its determinant shows us how much the volume change. Obviously, on this, based on the physical grounds, the determinant f need to be a positive value, right? So that's so we are not allowing the volume to disappear. That also will help us to actually in the mapping to establish that the mapping between the deformed and undeformed configuration can be done, and there is no problem mapping each point from each point to individual point into the deformed state. All right, so we established one important properties of deformation gradient again. So we established that its determinant actually measures the change in the volume at a point. All right, so then next okay, in the next lectures we'll continue to consider the relationship with the change of the area at a point again, and the length or fiber or line element at a point. All right, see you soon.